All right, so how's everyone doing? Um, I wanted to actually, there's a lot of videos around the new Apple M1 Mac, a Mac Mini, and how good that is for kind of data science and machine learning. So I've loaded up my Mac Mini M1 here. As you can see, it has the M1 chip, 8 gigs of RAM, which you wouldn't think is a lot, but actually, um, for our purposes, it actually turns out to be quite sufficient for most of the data science kind of tasks that we're dealing with and the machine learning tasks that we're dealing with. Um, it has 256 gigs of storage, as you can see, so 251, but it's actually 256 as advertised. So actually, I know there's a lot of videos on kind of scikit-learn and Python and so forth, but I wanted to actually work with R, as you know, R is pretty popular still for data science. It's definitely better at doing some of the data science and machine learning tasks than Python and scikit-learn and all these things. So I actually wanted to work with R. And so initially, if you just go to the RStudio page and you can download R, as is pretty standard. If you do it this way, what will happen is it will download the kind of Intel-based binaries. So if you download the standard packages, and if you do that, what will happen is it will run in the Intel-based framework. So it won't actually use the Apple framework. It will instead use the Intel framework, which relies on Rosetta. So actually, that's really good from a certain perspective, that that all of your R code that you've already written or stuff that you run in RStudio, it'll actually work flawlessly on the new Apple Macs as well. But it won't make use of the new Apple processors, as it will still rely on the Rosetta 2 framework to translate that code over to make sure it works. So given that, actually, I wanted to use the Apple Silicon and not have to rely on Rosetta. And so you can either compile the source code from scratch on Unix, or you can go to this great website. So, Mac, our project, which is run by very talented developers and computer scientists that are specifically dedicated to making sure that versions of R actually work on Mac OS. So you can see that they have kind of the standard older versions of R. So I believe we're at 4.03 right now. So they have, x86, which are the Intel machines, the 64-bit packages. You can compile it or just run the package installation file. But, we're mostly interested in 4.1, which is on Big Sur, which is what we're running now. And then the ARM, you can see it's for ARM64. So you can actually just download that and you can extract it into your source directory, and it will actually give you access to running R using the Apple Silicon. So let's do that. So I'll put this link in the description, but you can see that they compile it nightly. So I can do that. So if I just download that. It's downloading, as you can see. Okay, great. So it's downloaded. So it's pretty simple. You just go into your terminal, just run some Unix commands. So let's go inside downloads. Yes, it's rdevelop.tar.z. So all you do is you sudo into unpacking this tarball. So z r.develop.tar.gz, and this will basically allow you to extract it to your home directory. So it's going to ask you for a password, which I will type, but now I realize that. Okay, and so you can see it's extracted all of that. So actually, it's very interesting. If you see, it extracts to the system library into the framework. So if you actually those who are familiar with how R is installed, it always extracts the versions into the system library frameworks folder. So that's, you can see it's extracted. So there's a bit of a shortcut if you want to run R within your downloads folder, or you want to add it to your path. So what you can do is you can create an alias. So I'll show you how to do that. So I can, and that's not right. Sorry about that. Okay, so you can actually see that I've created an alias beforehand because I knew I was going to be making this video. And so I will use the aliases R-ARM, and basically this will call R, the 64-bit ARM version, in anything that you're running against. So I'll just compile that, and now I'll just okay, and now see if you run R-ARM, it will actually run the full 64-bit version, and you can see that it's Apple architecture, Darwin 20, and it's fully running. So actually it's really nice. And if you actually go into your activity monitor and you look at the processes that are running, so I can just show you that it's actually running inside Apple architecture, not Intel, aside from this. So let's just kind of print a giant loop, something like that, and then I can just go print I, and it's printing, and you can see that it's our process here, and it's the Apple architecture. So it's great. Now it's not running on Rosetta. It's fully within the Apple architecture. So that's really great. It's running all within the Apple architecture. So now let's do some kind of data science methodology. So there's an interesting problem that relates to Tic-Tac-Toe. So if you actually go inside the USCI machine learning repository, they have a Tic-Tac-Toe data set. And so I'll see if I can find it. I think it's this one. Yep, it's this one. So what this data set, it's really interesting. Given a data set of several player configurations and outcomes, it sees if the machine or if your data science algorithm can actually learn the rules of Tic-Tac-Toe. So basically, given all the data that exists, can you actually learn the rules behind Tic-Tac-Toe? So let's download this data set. So you can see that, if there's an X on one square of the top left square, you get an X. If not, it's an O. If it's a blank, then you write a B. So it's a multi-class. This is binary classification model. Positive means a win for X. Negative means a loss for X, or win for O. So it's all based on X. So positive means X is won. Negative means X is lost. So I can download that as well. So I just download it to my downloads folder. Okay, so it's downloaded it in the downloads folder. So I can go back into R. So I'm running everything in terms of the shell, which is okay. It's what it is. And I need two packages that don't exist in my installation because it's a fresh R installation. So one of them is to read the CSV file. And so it's going to ask me for a mirror to download from the first time. So I'll just pick in Canada because that's where I am. So it's going to say, in order to install reader, I have to install these other things as well, which is fine. I can just go ahead and do it. So you can see it's installing. You typically just have to do this for the first time. Now, if I was running RStudio, it would probably do all this for me, but it's just installing and running. So just let it go through the installation building of the reader framework. it takes a few minutes. And you can see it's all using the Apple architecture, so it's all using Apple. It's not using Rosetta at all, which is great. And so the reason why I say that is because although, as I said, it's fully functional using Rosetta 2, it's certainly desirable to test out the Apple framework and see it's done, and test out the power of the M1 processors. So we install one more package. So for this classification task, I'm going to use gradient boosted trees. So there's a nice, I won't use XGBoost. There's something that is also very powerful, and that's the GBM package, so gradient boosted machines package. And I'll install that as well. So what's interesting is that it has to build these packages from the source. So it's done. So you can see that I actually built them from the raw packages from the sources. It didn't download them from what we would find in standard Intel architecture. So let me kind of load them. So it loads that flawlessly. Like it's really great. Like it loads everything flawlessly, all and once again within Apple architecture. So it loads everything very nicely, actually, which is a really great relief that even within the experimental kind of M1 architecture, where you're compiling R sources from scratch, everything seems to work actually pretty well. So let me load the data set in. So I'll call it Tic-Tac-Toe, and it's just read CSV, and then I think it was called tic-tac-toe.data, so it's in my downloads folder. So downloads, then it's just tic-tac-toe.data, and see it reads it fine. So actually, you can see that the data set is fully loaded, and you can check the tail as well, but there's no need to really do that. So you can see, like, I don't like these column names, so I'll just change them. So they should be, there's 9 of them. It should be reflective of what the significant column names are for the data set. So I'll just kind of edit them really quickly. So tic-tac-toe, and then we'll just, so the first one is called top left, then you have top middle, top right, middle left, middle, so the most middle square, middle right, bottom left, bottom middle, bottom right, and then the final one is just the actual class, so I'll just call it result. And so now if I check, it's all good. Okay, so as you can see, all the column names have been updated. So so now what I can do is to actually run a gradient boosted or machine learning algorithm against this data set. You can see that each one of the fields here, each one of the features are string type. So you can see they're all characters, which is a string type. So what actually I should do to do this is convert them to factors, or do some type of 0, 1, 2 encoding. So there's 3 of them for each feature, and then there's 2 classes. So what I'll do is I'll apply encoding or factor encoding to each one of the features. So it's pretty easy to do that in R. So I'll make a new data set. I'll call it Tic-Tac-Toe mod. And then I'll just create a data frame. So I'll do it all at once, so I don't even have to apply to each one of them. So Tic-Tac-Toe, and then I want to call each one a factor. And you can see now it did that really quickly, right? So you can see they're all factors now, which is very useful. And so I said before that I'm going to be using the GBM uh, gradient boosted tree model, which is will be for binary classification. So you can, to do that, you need to actually do one more encoding of the factors. So it doesn't take in textual factors. It needs a numeric integer of 0, 1. So I'll just encode it really quickly. So tic-tac-toe mod of result. So, if let's say, we'll do it against the negative one. So if tic-tac-toe mod result is equal to negative, I'll assign this a value of 0, and if not, I'll give it a value of 1. So if you check it again, you'll see that it's been updated. Okay, right. So it's been updated, and so just out of curiosity, there's 957 rows. You can see, so 960 observations about. And so now I'll create my training and test data set. So I'll just make a random, let's say 80-20 split. So I'll just sample. And once again, I want to emphasize that like everything I'm doing right now is within the Apple architecture. It's not within Rosetta. It's all within the M1 chipset. So I can get an idea for how long this takes and how powerful it is. So 80-20 split, and then I'll create my training data set, which is just TRDF, tic-tac-toe mod ints, right? And then my test data set. Okay, so you can see I've created my training data set. So it has about 765 rows, and the test data set has 192. So it's a pretty decent split. And now I'll just do my gradient boosting. So let's call it GBM1 for my result. And so that's the GBM function. So result, and then it will be against all of the features. So I'm just going to use all 9 features that are in this. And my data set will be the training data set. And I have to specify a distribution of the response variable. So because it's a binary classification problem, I'll specify this as the Bernoulli distribution. And then I'll just start with, let's say, 2,000 trees. Let's make it an interaction depth of 4, which is, I think, should be okay. And let's run it. So there's running, and you can see it ran really quickly, right? So I mean, in some sense, you can see it's running in the Apple architecture. It only used about 10% of my CPU power, but you can say that, okay, it's because the data set is small, but like it's pretty decent. Like it's running quite fast, and it's running perfectly. That there's no errors, anything like that. So I can actually get a measure for how accurate this was. So let's predict against the test set. So new data is going to be in my test data set, and my type is going to be response. Yeah, I forgot to specify the number of trees, which I can do. Okay, and now I can just see, how many I got right. So what is my classification accuracy? And it will be of result. And if you notice, I've made a mistake here because I forgot to encode my classes. So I'll do that really quickly. So preds encode if else. So if preds is less than, let's say, 0.5, we'll assign it a class of 0. If it's greater than 0.5, we'll give it a class of 1. So you can see now they're all encoded. Okay, so now I can measure my classification accuracy. What is the class called? It's called result. And you can see we have 100% classification accuracy on the test data set, which is pretty remarkable, that it's able to actually learn the rules behind Tic-Tac-Toe kind of really quickly, and it was all within kind of nothing broke, like it was in the Apple frameworks. And what's interesting about gradient boosting is we can get a summary as well. So what's interesting, it opened it within quotes. So you can see the most kind of relevant feature for determining whether or not somebody will win the Tic-Tac-Toe game is the most middle square. So that has a 17.76% relevant accuracy. Then followed closely by the bottom left. So it seems like middle is the most relevant feature for determining whether someone will win a Tic-Tac-Toe game or not. But this is pretty cool. Like I'm pretty excited about this. So as I said, I was most interested to see whether or not the new Apple M1 framework could handle kind of machine learning tasks. And so like gradient boosting and doing a binary classification problem is a pretty standard thing to do. So if it can handle this, certainly it will have no problem with the other things that you can think of in R. And certainly when RStudio is available for this architecture as well, it will obviously just be like going from one system to another. So it's pretty great. I'm really excited about it. I'm also very interested to see that you're able to discern this information about how to win Tic-Tac-Toe, which is interesting as well. So yeah, that's it. So I wanted to just test that out, and it seems to be all in working order. I think I'll post more videos just to see how this will react to a bigger data set. So like if you had maybe a classification problem of 100,000 rows or something, how will that affect the training time? And how do the Apple processors fare under kind of larger data sets with only 8 gigabytes of RAM too. So let's see if we can push that, and maybe in subsequent videos I'll post that for you guys. But thanks for watching, and let me know if there's any questions in the comment section. I'd be happy to answer them. All right, thank you.